Okay, so in the previous video we said we would study the vector space over the integers of numbers of this form, right? So a plus b square root of 2, where a and b are integers. Obviously this is closed under addition. Well, we will now show that it's closed under multiplication, which is not incredibly difficult. So let's just see. Let's b, let's c, plus d. And this is a general multiplication of any two elements. And when we multiply it out, we get, and you can verify this by just multiplying out yourself, 2bc from these two terms, sorry, bd, and then plus the square root of 2 terms, which is square root, put square root 2 at the end, just like normal. And then this ad plus bc and square root of 2. And you see it's the same form, the numbers have the same form. So if these two are elements of, what do you call it? These two are elements of the vector space, sorry, the vector space 1. Sorry, okay, this is the set generated by 1 and square root of 2. And then this is also in the element of the set generated by 1 and square root of 2, okay? Easy peasy. Is it true that that this number is in this set, that the inverse of this number is in the set? And you might think, well, no, and the answer is no, it's not. For example, well, for example, 2 is in this, right? Because 2 is 1. Because we can just put the b is equal to 0 and a equal to 2, and we get 2. But there is no number of this form with the integer such that it equals 1/2, which is the inverse of 2, right? So this set does not contain inverses of numbers. So we've got the vector space, we've got that it is closed under multiplication and addition. What does that make it? Well, it makes it a ring. Well, it's got some of the properties that make it a ring, but essentially, because addition works and multiplication is closed under it, it is now a ring. So what we're going to call it is the ring of integers adjoin root 2. Why do we call it that? Well, clearly it's the smallest set containing both 1 and the square root of 2, right? Because this clearly has to be contained. So sorry, the definition of this z adjoin square root of 2 is the smallest ring containing, the smallest set, the smallest ring containing z and the square root of 2, okay? And so clearly this ring must contain this, because the rings are closed under addition, so it contains this. And also this happens to be closed under multiplication, and that means this is the this is indeed the smallest set that contains integers and root 2 and is a ring, okay? And so that's going to be it for this video. We've just shown that that the integers adjoin the square root of 2 is a ring. So in the next video, we'll actually go back to the vector space idea, and we want to define. So in the complex number, so we have something called a modulus, and kind of inspired by the Pell equations, we want to come up with a modulus for this, although it won't work quite the same way as the modulus in the complex numbers.